Hey everybody, this is section 1.4 and we're talking about polygons. On this slide we're going to define a polygon. You can see at the top of the slide on the left we have some examples of polygons, and on the right we have some examples of things that are not polygons. Well, what's the difference between them? Well, on the left we have some figures. They're all closed, meaning their sides are all connected. And on the right, we have some figures that some are closed, some are not, some are rounded, some are not. So that leads us to the definition that you see here. A closed figure in a plane formed by connecting line segments endpoint to endpoint. Now the definition of a side is each line segment. And the definition of vertex is each endpoint where the sides meet. So how do we classify polygons? Well, you classify a polygon by the number of sides it has. Familiar polygons have specific names listed in this table, which we'll go over. The ones without specific names are called n-sided polygons or n-gons. For instance, a 25-sided polygon is a 25-gon. Now you know many names of these different polygons. For example, a 3-sided polygon is a triangle. A 4-sided polygon is a quadrilateral. A 5-sided polygon is a pentagon. 6-sided polygon is a hexagon. 7-sided is a heptagon. 8-sided polygon is an octagon. A 9-sided polygon is a nonagon. 10-sided polygon is a decagon. An 11-sided polygon is an undecagon. 12-sided polygon is a dodecagon. And finally, of course, the n-sided polygon is an n-gon. Next, we're going to talk about how to name polygons. To name a polygon, list the vertices in consecutive order. You can name the pentagon below pentagon A, B, C, D, E. So if you look down at the diagram real quick, you can see A, B, C, D, E. We're naming by the vertices in consecutive order. You can also call it D, C, B, A, E, because that would also be in consecutive order. But you cannot call it B, C, A, E, D. That would be an incorrect name for this polygon because you're not naming the vertices in consecutive order. When the polygon is a triangle, you use the triangle symbol. For example, on the right, triangle ABC. Now, if it's not a triangle, we don't have a symbol and we must write out the name of the polygon. For example, pentagon ABCDE. On this slide, we define a diagonal. A diagonal of a polygon is a line segment that connects two non-consecutive vertices. So you can see an example of a diagonal in the figure below. Line segment DF is connecting two non-consecutive vertices. Convex and concave polygons. A polygon is convex if no diagonal is outside the polygon. You can see the polygons on the left at the bottom. In each case, every diagonal falls inside or on the polygon. Therefore, these are your convex polygons. A polygon is concave if at least one diagonal is outside the polygon. So look at the examples of the polygons on the right. You can see in each example, at least one of the diagonals falls outside of the polygon. Therefore, these are the concave polygons. Congruent polygons. Two polygons are congruent if and only if they are exactly the same size and shape. Now, if and only if means that the statements work both ways. For example, looking below, the first statement here says, if polygons are congruent, then corresponding sides and angles are congruent. But with the if and only if, we can reverse those two and state if corresponding sides and angles are congruent, then polygons are congruent. For example, if quadrilateral CAMP, which we see down here on the left, is congruent to quadrilateral SITE, down here on the right, then their four pairs of corresponding angles and four pairs of corresponding sides are also congruent. And you can see that based on the markings. So angle C, which corresponds to angle S, is congruent. Angle A corresponds to angle I, and they are congruent. Angle M corresponds to angle T, and they are congruent. Angle P corresponds to angle E, and they are congruent. Side CA corresponds to side SI, and they are both congruent. Side AM corresponds to side IT, and they are both congruent. Side MP corresponds to side TE, and they are both congruent. And finally, side PC corresponds to and is congruent to side ES. Now this final sentence up here is extremely important, so we're going to read it very carefully. When you write a statement of congruence, always write the letters of the corresponding vertices in an order that shows the correspondences. So if we look down below, here's our statement of congruence. Quadrilateral CAMP is congruent to quadrilateral SITE. Now this statement has been written very carefully because it shows correspondences. C and S correspond to one another. A and I correspond to one another. M and T correspond to one another. And finally, point P and point E correspond to one another. If you do not match up corresponding parts in your congruency statement, then you have written an incorrect congruency statement. Here's an example. Which polygon is congruent to ABCDE? Now, if you're watching this, pause the video and answer the question for yourself before listening to the answer. In order to solve this problem, I first need to look at the four different polygons. Which of the two, or which two, are congruent to one another? Well, I have ABCDE on the left, and then the second polygon I have, I'll call it JK, what is that? FGH. And I know that those are not congruent because I don't have congruency marks here. Let's look at the third one. LMNPQ. I'm matching up angles, congruent, 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 and then I check all the sides. Each of those have one tick mark, two tick marks, three tick marks. One tick mark, two tick marks, three tick marks. it appears that this is my corresponding and congruent polygon. So now I need to write my congruency statement. They've already started it for me up here. ABCDE is congruent to. Now I need to write this polygon name correctly by matching up corresponding parts. So A corresponds to N, B corresponds to P, C corresponds to Q, D corresponds to L, and E corresponds to M. I've written my congruency statement by matching up the corresponding parts. Perimeter. Perimeter measures the length of the boundary of a two-dimensional figure. The perimeter of a polygon equals the sum of the lengths of its sides. I'm sure you're familiar with perimeter. In order to find the perimeter of the polygon shown here, we're simply going to take all the side lengths and add them together. So we would have 15 plus 5, which is 20, plus another 5, which is 25, plus 12, which is 37 centimeters. Next, we're going to talk about what we call special polygons. The equilateral polygons. So on this slide, on the left, you can see examples of equilateral polygons where all sides are congruent. And on the right, we see examples of not equilateral polygons. Either all sides are congruent, or, in this case, it's not even a polygon because it's not a closed figure. So let's define equilateral polygons. They are polygons in which all sides have equal lengths. Equiangular polygons. On the left, we have examples of equiangular polygons. You can clearly see that all angles are congruent. On the right, we have some examples of polygons that are not equiangular polygons. So the definition, equiangular polygons are polygons in which all angles have equal measures. Regular polygons. On the left, we can see 3 examples of regular polygons. If you look closely, you can see that all the angles are congruent and all the sides are congruent. On the right, we have some examples of polygons that are not regular polygons. So by definition, regular polygons are polygons that are both equilateral and equiangular.